Hello and welcome to session 6 of Unit 3. This session will introduce you to nuclear fission and nuclear fusion reactions. By the end of this session, you should be able to state the differences between nuclear fission and nuclear fusion reactions. You should be able to explain the properties of nuclear fission and nuclear fusion reactions. We shall begin by looking at chain reactions. In order for fission and fusion reactions to be understood, we need to first understand chain reactions. Chain reactions are referred to as chemical reactions in which molecules undergo chemical reaction after one molecule becomes activated. So you need one molecule to start the reaction and the process continue by itself. There are two kinds of these chain reactions and they are the fission and the fusion reactions. Let us consider the fission reaction. So we can call them nuclear fission reactions. They are continuous processes, and in this process heavy atomic nuclei, mostly nuclei with atomic number 80 or more, split into a nucleus of intermediate mass, and these nuclei into which they split are known as daughter nuclei, and the nuclei that splitted are known as parent nuclei, and they end up emitting one or more neutrons. They are said to be continuous process because the reaction continues on its own when one nuclei splits to produce neutrons. The neutrons will initiate another splitting reaction, so the reaction continues. This results in the generation of energy which is called atomic energy, which mainly ends up as a heat. Some fission reactions are spontaneous while some are not spontaneous, and so the non-spontaneous ones require activation energy or requires to be activated by bombardment. Let us look at fission reactions in details, and we will use uranium as an example. In general, when large atomic nuclei are hit by slow-moving neutrons, they can become highly unstable if the neutron is absorbed by the nucleus. The large unstable nucleus breaks into two smaller daughter nuclei and also releases more neutrons, as well as beta, alpha particles, and even gamma particles. With the use of uranium as an example, when you look at the sketch below, you realize that there is one uranium nuclei which is bombarded. So there is only one uranium nuclei which is bombarded by a neutron. Now this neutron is absorbed into the uranium, which causes the uranium to break into two daughter nuclei, the lanthanum and then probably bromine. These two daughter nuclei are also unstable, which will also bombard with some of the neutrons that are released in addition to the daughter nuclei to form other nuclei themselves too. So they also break into two other nuclei, and those two other nuclei will also bombard with accompanying electrons. They also break, so the process continues like that. Now the neutron must be slow moving to be absorbed by the uranium, and as far as unstable nuclei are produced and neutrons are also produced, the reaction will continue. The overall process is called nuclear fission, and because it is accompanied by enormous release of energy, it forms the basis of nuclear power stations. We have established that the nuclei must be bombarded by a slow-moving neutron, which will be absorbed into the nucleus to cause the disintegration. So also we can also say that the particles that can supply that require activation energy for the disintegration include protons, also alpha particles, and even fast-moving electrons. Despite the negative effects that nuclear fission can pose on human beings, we shall be looking at these negative effects shortly. The heat energy from nuclear fission helps to generate nuclear power, and this is very important in human daily life. Let's look at how this happens. So the heat energy from the nuclear fission process in the nuclear reactor is used to boil water, to make steam, to drive a turbine and electrical generator in a nuclear power station. This, in a nutshell, we can say is how a nuclear power station works. However, because of the large energy generated by fission reaction, the process leads to or can lead to explosion, and as such, nuclear fission reactions must be controlled. Now, to control it, we use a system known as nuclear reactor. We shall also look at nuclear reactor as we continue in this lesson. The nuclear reactors helps to control nuclear fission reactions because of some of its parts, which can actually be modified to control the reaction. The nuclear fission reactor contains or is made up of several different parts, and one of the parts is the uranium fuel rod, which it is usually surrounded by moderator material such as graphite or heavy water, and we surround it by this graphite or heavy water so that it can absorb some of the neutrons that are produced in the nuclear reaction, and by so doing we manage to control the nuclear reaction. But this does not guarantee full nuclear reaction control. We cannot completely control the nuclear reaction by surrounding the fuel rod with the moderator materials. Another way we can also control the nuclear reaction is by using excellent moderators like boron. So when this moderator is lowered into the reactor core, it absorbs some of the neutrons that are produced, and this controls the nuclear reaction. It slows it down. If the reaction is becoming too slow, that is lower energy is being produced, the moderator can be pulled out so that the fission reaction can proceed faster to produce larger amount of heat. To the negative side of nuclear fission, we can talk about the invention of nuclear weapons such as nuclear bombs that can be destructive. Example is the fission bomb based on uranium-235, which was dropped in Japan city of Hiroshima in 1945, and the one dropped on Nagasaki, which is also made of plutonium, and both of these bombs relied on preventing fission happening until the bomb mechanism explodes a neutron source and uranium and plutonium metal into each other. Then fission will happen, and that will be totally uncontrollable. We said earlier on that one of the importance of advantages of nuclear fission is the generation of nuclear power. However, this generation of nuclear power in itself can also pose adverse effects on human life. And so there are some arguments against nuclear power generation, and they include: one, there is possibility of leak of radioactive materials into the environment, and this could be harmful to humans. This could lead to the cause of cancer and other forms of deformities and diseases in humans. There is also the difficulty of safety disposing of highly radioactive nuclear waste for a very long period. So the waste that are generated from these radioactive reactions, the nuclear reactions, how do we dispose them? That they do not continue, the reactions do not continue, and then the radioactive materials are not exposed to the environment once again. And this has been an argument against nuclear power generation. There is also a huge capital cost of building a nuclear power station, and the equal huge cost of decommissioning spent reactors. So, in order to put up a nuclear power station, a lot of money is involved, a lot of expenses had to be taken care of, and after the nuclear reactor is being used and has to be decommissioned, it has to be put out of use, it also becomes another problem because the nuclear reactor is now exposed to radioactive elements, and decommissioning it means that the environment is going to be exposed to these radioactive elements. Finally, another argument is the length of time for construction. It takes so much time to construct it, maybe 10 to 20 years to construct a nuclear power station. But to decommission a nuclear power station, it takes several years. And so this has also been a challenge that nuclear power generation poses on humans. Nuclear power generation benefits people and provides a lot of job in construction, and when it's finished and is operating, a lot of people benefit and get jobs, and people also benefit from the energy that is produced. But running a nuclear power station is not without risk. Example, there could be increase in background radiation exposed to local inhabitants where nuclear power plants are stationed, and there will be risk of accidents. So to make any major infrastructure planning decisions to build a nuclear power station, you must weigh up the benefits, drawbacks such as cost and operating problems because of the complex technology and high safety standards and even the risks involved. Let us now look at one of the major challenges associated with nuclear power, despite the fact that it does not contribute to global warming. We discussed earlier on that one of the major challenges is building and running of the nuclear power plants. This is time consuming and highly expensive. Also, when this nuclear power plant is out of use, decommissioning it is also another issue, which is also very highly expensive and time consuming. So, how then do we address this problem? How do we deal with the radioactive waste that are gotten from these radioactive power plants so that it will not affect human lives? One of the ways is that the radioactive waste is taken through the process of verification and stored in a securely sealed steel cylinder. To do that, the waste is mixed with ceramic producing materials and melted to form a sort of glass. The liquid glass form is poured into steel cylinders, cooled and securely sealed. The containers are then stored in a suitable waste dump which doesn't have to be underground. Now, the idea of doing this is that it is very difficult for the radioactive material to diffuse out of the glass. Another approach is that the radioactive waste can be stored in thick metal containers and buried deep underground with tons of protective concrete, so no dangerous radiations ever reaches the surface of the earth. Let us now look at nuclear fusion reactions. Nuclear fusion reactions refer to the coming together of smaller atomic nuclei to form a heavy nucleus. A typical example of this is the coming together of deuterium and tritium to form the helium atom. And when these nuclei are formed as a result of fusion of smaller nuclei, it leads to the emission of neutrons. So in the reaction equation that we have here, you can see a tritium being fused with a deuterium, and this will form the helium atom with the emission of a neutron. To produce a self-sustaining reaction, you have to provide the particles with enough thermal energy so that they can fuse with when they collide. And the deuterium to tritium reaction has an ignition temperature of 10 to the power 8 Kelvin. And so high amount of energy is really required in order to fuse these nuclei together to form the heavy nucleus. Now, when you consider the implications of these kind of reactions, you can begin to think or understand that these are basically thermonuclear reactions, and you can think of why it is so difficult to produce in a controlled manner. For example, the deuterium to tritium reaction requires that we fuse two positive charge particles. This means that we must provide enough energy to overcome the force of repulsion between these two particles that are both positively charged. And so high amount of energy is required. Each fusion reaction is characterized by a specific ignition temperature, which must be surpassed before the reaction can occur. In hydrogen bomb, for instance, a fusion reaction produced by a small atomic bomb is used to heat the content to the temperature required to initiate the fusion. And this is basically what happens in the atomic or the hydrogen bomb. We have established early on that each fusion reaction is characterized by a specific ignition temperature which must be surpassed before the reaction can occur. And we looked at deuterium to tritium reaction, which we said has a ignition temperature above 10 to the power 8 Kelvin. This is an enormous amount of temperature. However, any substance at temperature approaching 10 to the power 8 Kelvin will exist as a completely ionized gas or isomer. So this poses a challenge to nuclear fusion reactions, because it is very difficult to obtain this temperature under controlled conditions. And so there are several researches on nuclear fusion, and the goal of these researches include: 1. To achieve the required temperature to ignite the fusion reaction. So how then do we achieve this 10 to the power 8 Kelvin temperature so that we can cause nuclear fusion reactions to occur? Another challenge has to do with how to keep the plasma together at this temperature for long enough to get useful amount of energy out of this nuclear reaction. The other issue too has to do with the fact that if we are introducing this high amount of energy to cause the reaction to occur, then how then do we carry out this reaction to give us an energy that is more than what we are inputting into the reaction? And these are the researches that are ongoing now around nuclear fusion. In this slide, we want to look at how to address the challenge involving the enormous amount of temperature that is needed to start a nuclear fusion reaction. We've stated that to start a nuclear fusion reaction, we need about 10 to the power 8 Kelvin temperature and above. And any nuclei at this temperature will exist as a plasma. So how then do we do these reactions involving these plasmas? Now, one of the solutions suggested by scientists or researchers is the use of plasma containers such as the magic field. So they predicted both the donut shaped and the linear magic bottles to be used as nuclear fusion reactors. But the issue is that the reactors that produce high enough temperature for ignition are not the same as the reactors that have produced long enough confinement time for plasma to provide useful amount of energy. And so this solution seems so far from solving the problem. Another suggestion they made is if we can heat the 4 pellets containing the proper reagents for the thermodynamic nuclear reaction with pulse of beams of laser power, this can do the magic. And so if enough power is delivered, the 4 pellets would collapse upon themselves or implode to reach densities several orders of magnitude greater than normal, and this will be able to generate that enough energy for the nuclear fusion reaction. So as I said, this could produce plasma both hot enough and dense enough to initiate nuclear fusion reaction. These are self-assessment questions I have attached to this session, and I want you to try your hands on them.